Okay, great. So thank you for the introduction, Diane. So it's a pleasure to be here. And so thank you for inviting me, of course. So what I would like to talk to you about today is, well, 3D geometry and where I think it may be going. So that's a slightly whimsical title of the presentation is coming from. And so, you know, these are 3D objects, but are they? Well, not really. So if you know how these things are being generated, actually these are 2D videos look-alike. So these are things that a machine has thought of or dreamed up from textual prompts that look like they have a 3D structure to them, but actually they don't. At least they don't have an explicit 3D structure. These are just like videos, just exactly. These are 2D videos. And so again, so the idea here, you have a 2D prompt, could be an image, a frontal view of the object, and then there is a neural network there that is capable of sampling one of the possible multi-view sequence of images that would represent this object as if you were turning around it, right? And so when you look at this, you start to think, all right, so do we really need 3D geometry or not? At the end of the day, with this kind of model, everything is implicit in the network. You still get something that looks like 3D, but you don't really have 3D in any sort of explicit sense. But maybe that's good enough. So do we still need geometry? Well, I would argue that in many senses, yes. For example, if you wanted to 3D print this object, you wouldn't need to have a 3D reconstruction of it. But maybe you could do the 3D reconstruction on top of these images. So it's still unclear exactly where geometry goes. Even if you need it at the output, maybe you don't need it into the model. And so a few years ago, we started to think on these lines and try to explore the space and see where this could actually go. And so we started from the classical computer vision problem of structure for motion. So the problem of given a sequence of images like that, get to the 3D ground truth or the 3D structure of the scene that is contained those images. And the way you would actually normally approach this in traditional computer vision would first you would establish some correspondences. And this you would run some sort of pairwise model here that could be handcrafted, could be SIFT, or could be something, yeah, in this day and age, something learned, like superglue, for example. And that would give you correspondences between the images. And then on top of that, you would have something that is derived from visual geometry. Basically, you get a bunch of equations that explain how these correspondences arise from a three-dimensional scene. And given those inputs, you can solve those equations to recover the three-dimensional structure of the scene. And that's fine. But you notice I have colored these two boxes with two different colors. One is white and one is yellow. And that's actually going to be important in a minute. So particularly, the white box here is something which is handcrafted or learned. So again, it could be SIFT, could be superglue. But the stuff in yellow here is not necessarily learned, usually it's not, in fact, is a form of optimization. Could be, you know, bundle adjustment, for instance. So some form of large-scale optimization, maybe use a factor graph here. And there is tons of very interesting technology that goes into building these things at scale and making them work well, robustly, efficiently, etc. But now we have two different things. We have the white boxes and we have the yellow boxes. And, you know, maybe you don't want to mix colors necessarily. Now, if you fast forward in more recent times, networks have become more powerful. So, for example, you can take a network that takes a pair of images, not just one, but a pair, and gives you some information about the 3D structure of them. Could give you an estimate of the cameras, could give you an estimate of the depth map, and this has been going on for a while now. And more recently, and I think the community has a big depth here to NAVER, with you know, the idea of point maps, which was, if not introduced by Duster, definitely showed to be you know, a workhorse for 3D computer vision by Duster. And so the idea here, and we're going to dive into point maps much more later. So, but the idea here is that given the pair of images, you extract some representation of them, which captures the camera correspondences, the camera intrinsics, as well as the dimensional structure of the scene. So in one go, you get all sorts of this useful 3D information without having to run optimization. So just feed forward. That's very interesting. But this still didn't quite escape the predicaments where we were before, because Duster, though it's really cool, is still pairwise. That is to say that the part that is the neural network still takes pairs of images and outputs some results of pairwise analysis. And if you want to reconstruct more than two images, then you're still going through a process of optimization. Now, there is nothing wrong with it. And as Mark was pointing out before, if you really want to go a large-scale reconstruction, essentially reconstruction of a large area, you probably still need to do this even today. But again, you're mixing two colors, white and yellow. And again, I don't like to mix colors. So what we would try to do, and that was actually about a year ago. So this paper is 1 year old now. We wanted to try to do geometry in one go. So what this means is that you have a bunch of images as input, you have a big transformer, as generic as possible in the middle, and as output, you get all you want. So you get camera reconstructions, intrinsics and extrinsics. You get depth maps, you get point maps, you get correspondences. Basically, all the things you would need before you would get by a combination of learning as well as optimization, try to do them directly with a single transformer. Okay? Now, of course, I guess this model has been around for a while, so probably you've heard about it. It's called VGGT, which stands for Visual Geometry Grounded Transformer. Also stands for transformer we did in the VGG, which is our group. Okay, it's not a coincidence. Think about that. And so the way this works is you have a bunch of input images. You patchify them because you put them into feature extractor. We use Dino V2 for this. Then you get a bunch of tokens. You add these things here in red, which we call camera tokens, that are going to be used to represent cameras. And then you slap this into a big transformer, which has very generic structure, not entirely generic, but fairly generic. And this processes those tokens for a while. And off you get with this process dense tokens, the ones that you extract from the image, and the camera tokens here. And so from the camera tokens with suitable heads, you decode the cameras, and with another suitable head here, which is a DPT head, you decode the dense tokens here into depth maps, point maps, and also features you can use to establish correspondences between the images. Okay? Now, I don't want to make too much of a story about this, again, because probably you have heard about it. But so again, I think one point that we wanted to make with this paper is that we can keep this architecture as generic as possible and still get very good results in 3D geometry. So here, as I said, this is just a standard transformer. The only thing that is not standard is that we alternate global and frame attention. So global attention means that the tokens attend each other globally across all the images. And frame attention means that they attend each other only within each image, right? And the reason why we do this is because in this way, you give a chance to the transformer of being aware that there are, in fact, different images in the data. Otherwise, this would be just a stream of tokens. The transformer is permutation invariant, unless you add something to the tokens that tell the model which images they're coming from. You don't want to do that because it's nicer if you don't. And also, you get a model which is insensitive to the order in which you feed the images, which is something you want. So instead, what you do is you simply break the globality of the attention here, make it local, and this is enough to actually make the model aware that different tokens mean different things because they come from different images, okay? And that's it, that's the design. So this is some examples of the results you can get. So 32 views, half a second, this is the reconstruction you get. And then, let's see, maybe there's a couple more little demos here. So 64 views, you get a reconstruction, that's what the output you get. And again, this is feed forward to a transformer. Maybe I'm gonna show this in a minute in practice. And it works well, and it works also for more views, so up to a couple of hundreds actually. It also does things that are not possible with traditional methods at all, like for example, single image reconstruction. The model is always trained with 2 or more images, but somehow it acquires a pilot that allows it to also do monocular reconstruction like this. And so, of course, this you cannot do with a model that is not trained, is not learned from data. And so I think the message that we wanted to send with this paper at the time was that, so these are methods that existed before that use machine learning, but also use optimization to get their numbers up. Or maybe they need to do that because they need to glue together more than 2 images. At the same time, there were other works concurrent to the VGGT that tried to do this without having bundle adjustment, and it was already plateauing here. So they were getting very competitive with methods that would actually use optimization. For VGGT, though, we were able for the first time to really outperform those. And then if you add bundle adjustment on top, you can do better still. So it's not like the transformer is able to completely do the job of an optimizer, but it gets you to a point that's very important where the quality is enough for many applications, all right? Now, the other thing that VGGT had to it was that it was good at many things. So you do camera prediction well, point map prediction well. It also is very good at multi-view stereo, although it was not trained specifically for that. It's good at monocular depth, it's good at 2D matching, it's good at 2D tracking. So it has this sort of feel or vibe of being a little bit like a foundation model for geometry, right? And so, but to me, the most important thing, again, is why do we want to get rid of 2 different kinds of boxes? Well, this is my sketch of an explanation of why that's important. So here is a big transformer that could be your language model, say Gemini. And then you have text, you encode it, you slap into the model through tokens, and this does something interesting for you. Now you have another modality, it could be images or videos. You get another encoder, you get some tokens, and you slap them into the transformer. You get audio, same story. And now you get multiple views. And if you do it in traditional way, at the end of the day, what you get here is an explicit 3D representation, but maybe also involves having some optimization here. That is not that nice, because now the nature of this box is very different from everything else that exists here. It speaks a different language. It speaks the language of optimization. Everything else here speaks the language of TensorFlow, right? Or PyTorch, I should say. So you don't want to mix these two words if you don't have to. I mean, you can, but if you don't have to, it's easier. But most importantly here, you have 3D primitives, and there's not that always how you slap them into a transformer to actually do things with it. But if you have something like VGGT or one of the follow-ups or precursor models that try to work in this manner, then what you can do is you can get multiple views. You have an encoder that gives you 3D-aware features, but these are tokens, and they're very easy to add to the transformer together with the other modalities to start to reason in 3D with these big models, right? So I think this is an easy way of getting this multimodal model to add one more modality, which is the 3D modality, okay? And, I believe this is a reasonable approach. And so here, the point is that once you have this representation, which you could call the spatial representation, what is the exact 3D representation doesn't really matter. So you can have multiple views, point clouds, 3D meshes, volumes. You're going to have different encoders that map you into this set of tokens. And then if you want to generate something, and we're going to see an example of that later, well, you can take these tokens and you can decode it into multiple views, point clouds, 3D meshes, and volumes. So it becomes essentially representation agnostic from the viewpoint of the representation you interact with as a user. So the representation you put into the model and the representation you get out. And that actually has a nice property that it can be interpretable, very useful, right? Although the representation that actually goes into your big multimodal model here might not be interpretable at all, okay? Now, this is fine. What time is it? So how much time do I have? We started 10 minutes late, right? Okay. So I just wanted, I mean, this is just to break the monotony of my voice, just droning around, droning for a while. So this is just a little demo. I like to show VGGT. I mean, it's not that new anymore, right? So, I mean, you can probably do even better. Well, you can certainly do better things now because the model is 1 year old. But just to give a feel for what, does it say images there? I cannot see. Oh, wait. No, here. Okay, there you go. The hard thing of using the demo like this is, yeah, okay, so this is, hopefully, if the internet works, uploading the images to Hugging Face. And the internet's not working. Is it? Nope. Okay. It is? Okay, okay, good. So I took these pictures from this morning, from breakfast. So you do reconstruction. Yeah, that's what you need to do, right? So you need to show to people that, yes, this actually works. I'm going to reduce this, I'm going to mess around with these bars to get a few more points into the visualizer as soon as this. Okay. Did I press? No, reconstruct. Okay, great. All right, so now it should be reconstructing, I hope. Processing. There you go. This is done now. And yeah, okay, let me just try to visualize this. Yeah, 2020 or so. I tried this before, obviously, right? So I'm not completely suicidal, but yeah, let me see what I can get in. Yeah, so you can see that, I don't know whether this is exactly GDPR compliant. I hope nobody here in the picture is going to sue me. But you can see the sort of reconstruction you can get. So these are 5 images or so that I can reconstruct with a transformer basically right away, and you get pretty reasonable reconstruction, I would say. Okay? I mean, obviously it's not completely perfect, but given that there is no optimization here, I think this really conveys the idea what you can do with these transformers now. And of course, if you look at the literature now, you're going to find things like PyCube that work even better. And who knows, maybe something else from our group eventually that's going to be better than that, I hope. We'll see. Anyway, let me close the demo and let me carry on with the presentation. So here, but the world is dynamic, right? So, and I think 3D starts to get really interesting when there is motion. Why is that? Well, you want to use 3D maybe for robotics, and if the world doesn't change, the robot is completely useless, right? The robot is about changing the world, affecting it in some ways, and that basically means that you have to have the ability of handle dynamics. Also, if you want to learn physics, it makes sense only if the state can change, otherwise there is no. I mean, physics is essentially a description of change, or maybe the condition when change doesn't occur, but mostly is a description of change. So anyway, so you definitely want to be able to interpret the world as a dynamic entity that you want to reconstruct. So this is a bit of work that actually we did in collaboration with NAVER, so I had to present it. It's also interesting work, I hope. So this is called Geo4D. It was presented at CPR this year. So the idea here was, all right, so by the way, this is not done with the sort of scale you can get in Meta. So we are, I mean, NAVER has reasonable scale, but yeah. not quite the sort of stuff we use for VGGT, which, by the way, is nothing by comparison to what you can use, apparently, which makes me extremely jealous. But OK. So what we said, but the other thing is not just about scale, but it's also about the scale of training data. So for static scenes, you can get by and use traditional tools like CallMap and try to build a data set of things from which you can learn a network, right? But for 4D, it's much harder. I mean, now you can, to some extent, with this stuff like Megasum, for example. But usually, you're not easy to collect 4-dimensional data. So what we thought is, people think that video generators are great foundation models for word modeling, for example. And we know that they have some implicit understanding of 3D because they can generate images that when the camera changes viewpoint, then they look very reasonable. So we thought, let's start with a video generator, and let's try to repurpose that for the goal of 4D reconstruction instead. So we start from a model that does video generation, and we end up with a model that, given an input video, gives you a 4D point cloud here. So why doing that? Again, because you can take a model which is what's pre-trained on a large scale by somebody else, more than the scale you can afford. Videos can be trained on any image. Basically, you don't need almost any label to train a video generator. You don't need the 3D labels in particular. So it's very easy to pre-train a model like that. The video architecture is good to process lots of images. So you can take advantage of that as well. And then you also get stochastic inference, which is also very useful. If you think about it, when you do 3D reconstruction, what happened? Nothing good. Something bad. I mean, the image is still on my screen, but Okay. Haha. Yeah, okay, great, excellent. Probably the slides are just too awesome, I don't know. It's just broke the projector. Okay, anyway, right, so stochastic inference. So this is good because if you think about it, the 3D reconstruction is very ambiguous for monocular data. So you want to have that. So what we did here is to try to get, again, a video generator given an input video to give us 3D reconstruction in terms of point map, depth map, and ray map. And so these are actually redundant if you think about it for a second. So if you have point maps, you can infer depth and ray maps because we can reconstruct the cameras, and you have these two, you can get point maps. But just like in VGGT, if we found out that by predicting all of these things together, the model will actually benefit, probably because it has complementary supervision to an extent, but also because these representations, they tend to be generally complementary in some cases. For example, with depth map, you can, especially disparity maps, you can get nice close details, but maybe stuff a bit farther away is not represented as well. But point maps, they don't really work if you have stuff at infinity. So if you have sky, point maps don't make sense because the points are, well, you cannot determine where they are. But ray maps, they're fine. So it makes sense to use these things together. Okay. So when you do video generation, what you develop is a latent space here. So you get a bunch of images, you encode them into a set of compressed latents, then you can decode back into a bunch of images. If you, that's your goal, is to generate a video. And this latent space is compressed, and it makes generation much easier. So we said, let's take a pre-trained video generator as well as the encoder, and let's adapt it to encode instead point maps, depth maps, and ray maps, which at the end of the day, they are like videos. So point map is literally X, Y, Z. So instead of RGB, you have coordinates. You can encode and decode. It's not that easy. So Zeren, that is true, and actually did this. I had to sweat quite a bit to make this work because the modalities are not that compatible. But eventually, if you work hard enough, very hard actually, then you can make it work. All right. And once you have these latent spaces to encode these quantities, then there's a lot of detail in these slides, but it suffices to say that you put that into diffusion denoiser, so you can generate a video which consists of these modalities instead of just RGB pixels. And the way you condition this model is by providing to it an RGB sequence. So the RGB sequence is not generated now, but rather is the conditioning that goes into this model that takes these latents and denoises them to get your reconstruction you want. Okay? And so at inference time, you take the video, you have noisy latents, you denoise them as normally done in denoising diffusion, and then you decode your decoder, and you're going to get the point maps here. There is another thing here which is uncertainty, but I don't want to get into many details. And so when we did this model, one thing we got was very, very good dynamic depth. So this is a bunch of data sets, Intel and Kitty, and you can see that this at the time was the best. Okay, great. And these are a few examples. So you can see the reconstruction by a competitor at the time, which was Monster. And what you get here with ours, this is depth maps, obviously. And you can see here the flamingo, and you can see that somehow this model, which was pre-trained using a video generator, makes more sense to the legs as compared to what you see here. The model is very confused by the reflection. This one is less. So this is a thing you can do by repurposing a video generator. And then you can see this thing in actual 4D, if you like, or that is to say, with a disembodied perspective, so you can see the quality of the reconstruction, which is not bad. And here's one more example with the flamingo. Okay? But I need to press on because I want to show you quite a few more things. Now, do you think this is good enough for 4D reconstruction? What am I missing here? Do you think that if I reconstruct dynamic point maps, if I reconstruct depth maps over time, is that valid or sufficient for the reconstruction or not? No, obviously not. Otherwise, otherwise I wouldn't be asking the question. But what is missing? So let's see. So when you do a 3D reconstruction, these are examples of 3D reconstruction tasks. So you want to reconstruct static 3D points. Okay, that's obvious. You want to match image points. That's less obvious, but once you do the reconstruction, you get matching, and from matching you can get the reconstruction. So these things, I wouldn't say they're equivalents, but they're very closely related. The other thing you do is you reconstruct camera motion. So when you have a sequence of images, even if it is not changing in the world, well, there's one thing, it's the camera, right? So you reconstruct the motion of the camera. Now, when you have 4D tasks, when you have 4D data, you want to reconstruct the dynamic points, so the points they move in space. Okay, fine. So we get that with dynamic point. If we do depth at every frame, we're going to reconstruct those. You want to match the dynamic image points, though, and that's not obvious how you do that if you have depth maps. Okay, and you also want to reconstruct the scene motion. So you want to reconstruct how things move in 3D, and that, if you only have depth maps computed in every frame, you cannot do. Right? So we are missing these two things. And I think what we want is a representation of 3D, that is able to recover those two things in a natural way. Okay? And so this is the subject of the next part of the talk, which is what is a good 4D representation? Now, again, this is huge depth to Duster. And this is going to build on the concept of point maps. Right? So here you see a point map. This is a very simple thing. So this is a simple image. Every pixel you touch, a 3D point. Done. Right? It's a point map. Doesn't seem like much. But if you think about it from this, because these 3D points are reconstructed in the camera reference frame for now, from that you can already infer the intrinsics, which is interesting. But when this gets really interesting is when you have two images, right? And then you get the point maps from both of them, but you'll notice that the second one seems to be rotated. Why is that? Well, because here the camera viewpoints changes from image 1 to image 2, and the point maps, they are reconstructed in a viewpoint invariant manner. So they look rotated, but really what happens is that now if you take this and that, and you overlay them, then you see that the points here on the cube, for example, they match. Okay? Why is that? Because again, despite the fact that the camera is rotating, then the reference frame of the points that are being reconstructed is invariant, right? So these are viewpoint invariant point maps. And this is where you can really get the good stuff from Duster, right? Because now from that you can recover the camera motion, and you can also get this sort of unified point cloud reconstruction of both images, not just a single one of them, in a way which is aligned. Okay? And so let me just introduce a bit of notation to try to explain this better. So you have image I1, I2, and then let me zoom in here. We have two viewpoints, pi1 and pi2, and then here I have a symbol, which is just letter P, which stands for point map. And you see there is an index here, which is 2. That means that these pixels these 3D points are reconstructed from the second image. But you'll notice that the viewpoint comes from image 1, right? So this is actually crucial. So the point map here combines information from both images. It takes the pixels from this image and gets you the corresponding 3D points. But the viewpoint is the one from the first image, right? And this is what makes really these point maps powerful. Because once you have this, then you can get, again, all these kind of different reconstructions. For example, if you want to know that these 2 points, U1 and U2, are the same point in the 2 images, all you need to do is to compute the corresponding point maps. And because the 3D point didn't move, then the 3 points must coincide. And by checking the value of the point maps, if they're equal, then you know that these 2 pixels are in correspondence. So you're recovering correspondences from the point maps. Okay? Now, did you spot the problem with this? Yes. Okay. What's wrong? Which points specifically? Yeah, okay, fine. But did you see the points that moved? So the cylinder was moving, right? So you see here that the points on the cube, they overlap, but the points on the cylinder, they don't. right? And the reason is that the dynamics of the world, the fact that the cylinder is moving, breaks the invariance. So what we did here was to try to restore invariance. So this doesn't work anymore. And so you cannot, for example, establish correspondences anymore because of that. And so what we tried to do was to fix this. And this is this notion of dynamic point maps, which I think is actually quite useful. So what we did was to say, all right, let's now add to our point maps also the time variable here. It's a very simple extension. So from a single image here, if you have a pair of images as input, what you can recover are 2 pairs of point maps. And from each image, you're going to get 2 versions of the same point map at 2 different times. OK, let's explain this again with symbols. So you have image I1, I2, time T1 and time T2. There's also a poster. I think that's up to date. Sorry about that. There is also a viewpoint, pi1 and pi2. And now what you can get is from the first image, you can get 2 point maps. So you can see that the index 2 is the same as the image because these are 3D points that correspond to those pixels. But then the viewpoint comes from the other image, just like duster and master. But crucially, now you have the time, and the time is also mixed. So one point map here gets the time from one of the 2 images, and the other point map here gets the time from the other image, right? And with this fixes the problem. For example, if you fix the time to be the time image 1, then this cylinder is reconstructed back into the original position, although it's actually seen a different position in the second image. So you're undoing the effect of time, effectively. And this restores the invariance, which means that allows you to establish this correspondence. Okay? And then the other thing you can do is if you look at that single image here and you compute the point map from this image twice, changing time, what you get is a reconstruction of the scene flow, the scene motion. Because you can see as time changes how the points drift over time, right? And again, this is a simple extension to duster and master at the end of the day. And so there were other papers that did extension on duster and master to dynamics. The most famous one, I think, is Monster. And you can see that Monster has this pitfall that does not quite restore invariance because of dynamics. But with DPMs, you get 2 versions of these point maps that overlap perfectly, well, as long as your model can do it, perfectly, at least in theory, because, again, we control for time. Okay? And so we fix the problem. Now, the way we did dynamic point maps, that was also a year ago. Actually, it was before Monster, but the paper got rejected the first time. So what can you do? So we based this on duster. So that was before VGGT. So we take duster, we just add a head that trains to produce 1 more point map per image, and then you fine-tune your model on some synthetic data, and you get your model. So these are just a few examples of what this does, of what it used to do a year ago. Okay, so you can see you can reconstruct the camera. The scene is moving, and it does this sort of kind of like slightly shaky 3D reconstruction. Part of the problem is that we can reconstruct 2 frames at a time, but then to glue them together, I mean, you need to do some alignment and optimization, which is also something that we shouldn't do in theory. But most important thing is that we actually get 4D information. So now, because you get the scene flow, you can detect motion in the scene despite the camera motion, right? So the camera is moving, but you also know that this stuff is moving with respect to the camera. Because you have the scene motion, you can threshold that. And you can see here, maybe just barely, especially after the back, that we can reconstruct tracks as well. So these tracks are derived from the dynamic point maps directly. And so, okay, I don't want to make too long of a short story, but so if you try to reconstruct scene flow with something like Monster, you need to add to that something else, which is optical flow, or maybe a method for matching. And if you do that, it works less well than trying to recover dynamic scene motion directly with your dynamic point maps. Simple concept. Now, as I said, this is a year ago. What happened more recently? Well, we thought, okay, if we have VGT on one side, we have DPMs on the other side, we should really combine them. So that's what we try to do. This is the first time I showed these slides to anybody. I did them this morning during your talk, I have to say. So sorry about that. Anyway, so what we said, okay, so I hope you're good enough. But basically, the idea was, okay, let's then extend this concept so that instead of getting 2 images as input, we get n images like VGGT. So we take a VGGT backbone, and as output, we reconfigure, we just fine-tune VGGT to produce these point maps, P0, T0. There is also pi naught here, pi 0 everywhere, but the viewpoint is always the same. It's always the first image. So I don't need to pollute the slide by repeating pi naught everywhere. But each one of these point maps also has a pi naught, which is the viewpoint, which is the viewpoint of the first camera. That never changes, okay? But then from I0, I'm going to construct P0, T0 from I1, P1, T1, and from IN, P IN minus 1, IN minus 1, Tn minus 1. So what does that mean? So these are essentially like dynamic depth maps, except that they are point maps. So they're still reconstructed in a specific reference frame. But essentially, each one of them captures the time of the corresponding input images. And now VGGT doesn't know about time because it's trained on static data, but it's not too far away from what it can actually do already. So with a little bit of fine-tuning, you can get VGGT to try to understand dynamic content as well. This was done in Oxford, by the way, on a very small number of GPUs. But because the foundation, the VGGT is a good model as a foundation, it doesn't take too much to get it to do those things. Now, what we said is, OK, so now how do we extend this to actual dynamic point maps? So what we're doing here is we are taking these the tokens that represent these slices of dynamic point maps, and what we're saying is let's pick a reference time TR here. Let's put that into some other new layers that we train from scratch, and those will essentially take those guys and refer them back to a specific reference time. So essentially, you can think of this in token space, not in any sort of explicit manner, but you can think of that as taking those point maps that exist at different times and trying to make the time the same. So you're trying to establish correspondences through time and fuse the information. And that's done through these layers here. Okay? And now what you get is that all the point maps are referred to the same viewpoint and the same time for the entire video. And this is another way of saying that. So these are images, and these are the times that correspond to the different images. And you can take any image at any time, and you can get the corresponding point maps. Okay? What we do with this model is we reconstruct the stuff in a diagonal. So we let the image and the time change, covariantly, if you like. And then once we have done this yellow stuff, with another part of the model, we refer everything back to the same time in such a way that we get the green stuff instead. So we are compensating or registering for time as well. Okay? And this is actually a reasonable design because it's very easy to extend VGGT or models like that with this because it's a very minimal modification, but then you also get the benefit of reconstructing dynamics as well in the sense of the 9-point maps. And so, if you do the experiments here, this is 2 frames only. This is just to show that if you inject VGGT into the equation, then yes, the performance is a lot better than what we get without using VGGT. So this is compared against our method last year, then Star Trek and Trace Anything, which came out very recently. And this is just because the backbone is actually quite good. But these are some examples. Again, sorry if this is a bit rushed. But anyway, so this is a tennis sequence. You can see the reconstruction, and now you can see how we can recover for the emotion as well. And now you should be able to see the tracks quite well. Okay. Again, this is not something you can do if you only reconstruct that. And this goes on for a while, so I'm not going to show you all the sequences, but maybe another 1 or 2. So, and again, this was done in Oxford, not in Meta, so on a relatively small scale, just by starting from a good pre-trained model. And if you were to do this on top of something better than VGGT, I would expect it will work even better, by the way. Okay? All right, so how much time do I have? 15 minutes, I guess, right? 10? 10 minutes. Okay. Oh, yeah, because we started 10 minutes late, right? Okay. This is the last one. This is goldfish. It's a bit of a mess, but somehow the model can make sense of this as well. So you can see that the fish are reconstructed correctly, more or less, and they're traced correctly. And the background is really complicated because it's this aquarium. So it's not that easy to do. OK, so this is a VDPM. Now, the last 10 minutes I'm going to spend in trying to explain to you what I think where spatial AI is going, or what is spatial AI is for me, all right? And then I'm going to stop. So what is spatial AI? So spatial AI, again, I guess a lot of the definition we had today were about using this eventually for robotics, right? So something like this, right? So this is a video from Google Gemini, so not my work, but it clearly shows that even in their minds there is the fact that you should have a model of perception which is rooted in three-dimensional representations, right? So this should naturally be useful for something that interacts with the real world, because obviously the real world is three-dimensional, and physics is also easier to explain once you get to the third dimension as opposed to try to explain physics in the image plane. Okay? But really, there is more to spatial AI. So if you have a spatial brain, right? And one thing humans can do is to build things, right? So we can design machines, even that stuff doesn't necessarily work, but cool machines, and you can design buildings. So you have architects, you have mechanical engineers, you have civil engineers, right? And so what I think spatial AI is also a way for machines to start to speak about the language of building things that exist in the real world and can actually be useful for humanity, right? And then if you take this to the limit, what would it take to build an AI that then lands on Mars and builds a city for you from scratch and designs it entirely, right? So how can we get there? How can we get an AI which basically is like an army of civil engineers, for example, or an army of mechanical engineers? And a mechanical engineer is very interesting because he has the ability of designing things, but he also has he's also a human being most of the times, right? And that means they have eyes, they have language, they have an intuition about physics, but they also have the ability of connecting that to formal understanding, mathematics, and CAD design, etc. And so linking all these modalities together, I think, is really very exciting. And for me, that's one of the most interesting things about spatial AI is bringing these things together, right? The animal part as well as the intellectual part of how we think about space. So this brings me to generative AI. So that's the stuff we're actually doing in Meta. This is actually pretty old, but just to give a sense. So here's you get a prompt, you get a model that can spit out the corresponding three-dimensional object. And so this is not functional. It's just a pretty things you can put in a video game. Doesn't do anything. Maybe you can do a 3D print of it, but that's it. But still, that's where this is trying to get. And so the challenge with 3D Gen AI, as 3D AI in general, is that you have tons of training data for text, quite a lot of training data for images and videos, but you have very little data for 3D. And so this is maybe a way of looking at the problem. So there is a huge information gap between having a prompt, just a Phoenix robot, and having the actual 3D object. And your model somehow has to fill this gap, from low information to a lot of information here. And so you need to learn to fill this gap while having very little 3D data to train from. And that's actually very hard. So normally what people do is to break this in two stages. First, you reconstruct an image using an image text to 2D model, image generator. And then given the image, you go 2D to 3D, right? And that's actually much easier because the difference in information content is actually much less than you had before. And so here is where we can get enough 3D training data to actually train good models already. And so this is just to make the point that it's interesting to specifically to look at the task of going image to 3D, because this is where we have reasonable amount of training data and we can solve this problem actually quite well. Now, how is this done? Well, this is a 3D generation task. So you're going to have a prompt, which is an image, and then you have an object X that is what you want to generate. And really, this is very ambiguous. So you want to cast this as a sampling and distribution, conditional on I, of 3D objects. But the way you really do it is, I think a very good way of doing it is to go through 3D latent spaces models. And this is actually interesting because you start to build another kind of representation of 3D things, which is not explicit, but can easily be decoded into something which is very explicit and actually very useful directly if you have 3D applications. And so this is going to be an autoencoder. So you have a 3D object as input. You have an encoder that maps that into a bunch of latent tokens. You have a decoder that gives you back the 3D object. And there is a variety of these things you can use in the literature. One class, most of them actually are what I call translational, in the sense that you start from a kind of representation of 3D object, which is explicit, like 3D point cloud. Then the encoder maps that to latent tokens, and then the decoder maps that into, in this case, an SDF, which is also a representation of the three-dimensional shape of the object, but is of a different kind from the kind you had as input. So it's kind of like an autoencoder, but also translates between one modality and another. And I think that's this task of translation modality is also something that is actually useful to make this latence not that trivial. All right, so it helps the model to learn an autoencoder while also learning to translate between representations. And so which is the representation that we like? Well, we like vecset. Vecset is not our invention. That was done in TUM. And the idea is actually kind of very simple and very elegant in my view. So you have a 3D object, in this case a cube. You sample a bunch of 3D points, a point cloud out of them. And then you split that into what you call support points. So it's just a subsample set of 3D points you have here, and you're going to use those as tokens. And the rest of the point you have there. And then through some layers of the transformer and cross attention, you try to summarize the information which is left here, which is the majority of information actually, back into this set of support vectors or support queries. Support vectors, eh? Yeah. Okay, these are support vectors in a way, but not really. Okay, so, and then you get your code. And then once you have the code, you can query space, you can get a three-dimensional point, you can take your tokens, and your decoder is going to tell you the value of the F function of that particular three-dimensional location condition on the tokens that represent your 3D object. Okay? This is super simple, super elegant, and actually works quite well. So to sample this, you would train a usual diffusion model. So let me not go through that again, but basically it's just denotes in diffusion. And these are some example results you can get. Again, year old, now we can get much better, higher fidelity than this. Doesn't matter. The point is that you can take an image, you can get very nice 3D reconstruction, which are complete. Again, because the latent space is really a really strong prior. Okay? And here's some more examples. But 3D has a lot more than that. So what I think is interesting about 3D is that it's not just about shapes, it's also about structure. You have 2D pixels, that the equivalent would be 3D voxels, yes. But then you also have, for example, 3D cells in topology, if you're thinking about a mesh, something you don't have in an image usually. You have UV maps, atlases, and textures, something, again, you don't have in an image. You have, if you take a three-dimensional file like GLTF, you look at the structure of it, it's very complicated. And so all these are just to give a sense of the things that we might want to generate with 3D models, all right? And the last, so what that takes me to compositionality. So the bit of structure that we really want to tell you about is that, which is, again, something that does not really exist when you do image generation, but it can exist when you do 3D generation, because it's actually useful to have these components for various applications. And what we discover, this is a newspaper, is that vecset is actually highly compositional. So if you take the vecset of these two things together, and you just stack the tokens together and you decode them, then you get this. You get the composition of the two objects, and the composition can be actually very detailed and very geometrically accurate. So you can build on this to get things like automatic generation in a part-oriented manner. And so let me just skip over all the details, and I'm just going to show the results, what you can get with this. So you can take an object like this, you can reconstruct that in 3D, but by building on the fact that the vecset is very compositionally friendly, you can build an autoregressive model that can generate part by part and give you the composition of the object into the constituent elements. This is actually very useful in many applications, again. And here's another example. So you can take a scene like that, you're going to get a 3D reconstruction out, but you also get all the individual components too. And you can also start from an existing object scan. So this is an example from Google scanned objects. We put that into a model. Our model works in 3D, doesn't need an image, doesn't need anything, actually doesn't need, doesn't need SAM. Just looks at the point cloud, and automatically the transformer is able to figure out the components and give them back to you one by one. Okay? So it's actually very flexible. And here's one more example out of Google scanned objects. You can see the different elements. Okay, so sorry for being 3 minutes late. So what are the takeaways here? So I think I really like the fact that the geometry is coming back. It was sort of forgotten in computer vision while we were busy doing image understanding, but now it's coming back with a vengeance as mainstream. Part of the reason is that VLM has taken over the image understanding part, but they're not very good at geometry yet. And geometry is really needed for anything which is embodied. And that doesn't just mean robots, it also means, for example, designing and building things that exist in the real world. So models like VGGT, of which there are many follow-ups now, show that we can do a lot by having implicit representation of the three-dimensional world. I think this is a sign that I should stop. But my point there is that, this is really annoying. My point there is that you don't need the representation to be explicit within the model. You can still have an implicit model that operates on a space of tokens and still have very good input and outputs which are explicit in 3D. And then finally, again, let's go beyond just think about reconstructing an image or a video. Let's think about generating new things that will exist in the real world. I think that's very exciting, and that could open up a whole new space of very interesting research. For example, how are you going to build machines? Okay, thank you very much.